Hello everyone. In this lesson, we're going to have a comprehensive look at the GCSE topic, electricity. There are some things we need to solve first. The first term we need to get used to is the current. In a loop of wire, let's say from point A to point B, electrons will flow in that wire. And the flow of charges, be it positive or negative, is what we term as current. In fact, we're supposed to say that when we talk about current, our major focus should be on the movement of electrons. And how about voltage, or what we term as the potential difference? That is the difference in potential between 2 points in a circuit. It's more like we can say that it facilitates the movement of currents. So it's like a force that moves the current. And then the third term we need to get used to is what we call the resistance. Just before that, current is measured in amps, voltage is measured in volts, and the resistance is measured in ohms. Resistance is basically anything that slows the flow of charge around a circuit. Now, there is an equation that links these three guys. That's what we term as the Ohm's law. V equals IR. That's Ohm's law for you. The current is directly proportional to the voltage or to the potential difference, provided that resistance remains constant. Let's say we have a wire now, and then a current of 1.2 amps flows through the wire for 5 minutes. Now, how do we now determine the amount of charge that has moved through that wire in 5 minutes? And the quantity of charge is Q. That's what we need right here. So using this equation, Q equals IT, all you have to do is to plug in your values, and then you get your answer. The time is measured in seconds. Current is measured in amperes, and then quantity of charge is measured in coulombs. So you convert the time to seconds, times 60, that gives you 300 seconds. So Q equals IT, that gives 1.2 amps times 300, that gives 360 coulombs. So let's say that the charge here is 0.2 amps, and then the potential difference here is 9.4 volts. Now the question says that we've placed a resistor in this particular circuit, and we need to get the value of the resistor. Earlier, we talked about this equation for Ohm's law, that the potential difference is directly proportional to the current, provided that the resistance remains constant. Okay, provided we'll have a constant resistance. So here, let's work out the resistance for this question. That's V over I. V is 9.4, and then I is 0.2. That gives 47 ohms. Now, there are some substances that obey Ohm's law, and there are some that do not obey Ohm's law. Now, the substances, or let's say the components, the electrical components that obey Ohm's law, we term those as ohmic conductors. Okay, let's use a different color here. We term those as ohmic conductors. So on the y-axis, you have the current, and on the x, you have the potential difference. So ohmic conductors, there are components that obey Ohm's law. One more thing. the graph is usually a straight line graph that will pass through the origin. Those are ohmic conductors. And then some examples of that, we term this as IV graph. Some examples of that, we've got wires. Wires are ohmic conductors. And also, you've got heating element. Heating element are also ohmic conductors. And then on the flip side, we have what we call non-ohmic conductors. Non-ohmic conductors, for them, the current is not directly proportional to the potential difference. So here we're not saying it's inversely proportional, but the real deal here is it's not directly proportional. So having said that, we are not talking about a straight line graph here. So we have something that looks like a curve, potential difference here, potential difference. Yeah. So here, current increases here, the temperature of filament increases, and as a result of that, the resistance also increases. Now, this is it. There is a relationship between the current, the temperature, and then the resistance. Current tends to build up the resistance in a circuit, and once the resistance increases, the temperature would also increase. So it's more like when you have electrons here, all right, and then when you pass current across these atoms, the ions, the individual ions, they vibrate. So the higher the current, the higher the temperature. So these atoms will tend to vibrate more. And if there is an electron here trying to pass through these guys, it's easier for this electron to pass through when the vibration is not, that much. But when the vibration is much, the temperature will be on the rise, and so the resistance will also be on the rise. So invariably, when the temperature of a particular substance is low, it's more easier for the electrons to pass through because the vibrations will be less, and then there will be little resistance to the flow of that electron. So having said that, the basic examples of non-ohmic conductors, you have filament lamps, you've got diodes, and you've got thermistors. Thermistors, they're a type of variable resistor used in measuring the resistance of a circuit. So they respond to an increase in temperature. Once you increase the temperature in a thermistor, the resistance will drop. Okay, and for diodes, they convert AC, that's alternating current, to direct current. That's how diodes work. So let's move in from there. All right, let's talk about series and parallel circuits. If you have, let's say you have a circuit like this. Let's do it this way. We'll have the cell. Or it could be a battery, if you want to do it that way. So let's say we have a lamp, a second lamp, and a third lamp. Now, a series circuit consists of just one loop of wire. No multiple loops. We've got no 2 loops. We've got no 3 loops. Just one. All right. Now, the basic thing you need to know for your GCSE for as per a series circuit is how does current behave in a series circuit? How does potential difference behave in a series circuit? And how does resistance behave in a series circuit? In a series circuit, the current is the same everywhere. The current is the same everywhere. So the current the starting current is the same in every part. Is the same in every part of the circuit. Now, what are we saying here? We're saying if the starting current is 2 amps, if you measure the current passing through this lamp, it will be 2 amps as well. If you measure the current passing through this, it will be 2 amps. If you measure the current passing through this, it will be 2 amps as well. Now, this is dependent on one thing, that these 3 lamps, they have identical resistances. Okay, so now for the potential difference is shared between the components. It's shared between the components. So this is it. If the beginning potential difference is V, that's the starting potential difference, or what we say, the potential difference of the cell. That will be equal to the sum of V1 plus V2 plus V3. Now, one thing you should know is that potential difference is always connected in parallel to the circuit. That's why you can see that we're creating an extra loop here. That on one side. Then back to the resistance. The total resistance of 2 components is the sum of the resistance of each component. So here, let's say the resistance of this bulb is 2 ohms, and the resistance of this guy too is also 2 ohms, and the resistance of this is 2 ohms. All you got to do is just to do R equals R1 plus R2 plus R3. That's the summation of everything. And this gives 2 plus 2 plus 2. The total here is 6 ohms. What if we have a case of parallel circuits? What if we have a case of parallel circuits? How should we work that out? So let's draw our parallel circuits here. 2 loops, all right? Now, one thing you should bear in mind, for parallel circuits, they consist of more than 1 loop. So it can be 2 loops, it can be 3, it can be 4, it can be 5, or even more, depending on whatever we need. So let's say we've got a bulb here, and we've got the second one here. All right, so let's say the starting current here is I. That's the starting current. And then for this to be okay. And then we'll have I1, that's the current passing through that junction, and I2, that's the current passing through this junction. So let's go back to our definitions. For the current in our parallel circuit, the current is the sum of the separate components on each loop. So here, the total current is I, and that amounts to I1, that's the current in this particular loop, plus the current in the second loop. Now, if you've got like 6 loops, that would be the addition of the current for all the loops. All right. So let's say you've got 12 amps as the current, as the starting current. This guy will be 6 amps. This guy will also be 6 amps. All right. So the resistance is equal to the smallest. Okay, not even equal. So the resistance is less than the smallest individual resistance. So this 2 now, the smallest is 4 ohms. So the total resistance for this is less than 4 ohms. And mathematically, you can have this as the total resistance, that's the inverse, equals 1 over R1 plus 1 over R2. And then when you compute this, whatever you have as R at the end of the day will be your final resistance. So now let's talk about direct current and alternating current. A direct current, or sometimes can be called a direct potential difference, will produce current, and the charge carriers will move in one direction only. So let's say we'll have it like this. For the sine wave of a direct current, you have something that looks like this. Yeah, something close. And then that's for DC. And a typical example of substance and a typical example of components that use direct current. You have batteries. Batteries are DC. And for AC, that works differently. For AC, the charge carriers move in two directions. They're bidirectional. That means they move. Let's have something like this. Forwards and backwards. Something like this. That's for AC. And a good example of that is mains electricity. That's the power supply. And then, in the UK, mains electricity is supplied at a frequency of 50 hertz and 230 volts in terms of its potential difference. All countries have their now, one thing you should keep in mind is that the light in your houses, in your homes, the light may get dimmer or brighter depending on the times. Now, it gets dimmer when there is too much load. For example, let's say there is a football match and billions of people are watching that football match, let's say World Cup, and then at halftime, people would maybe go into the kitchen to put on the kettle, to switch on the cooker and do a lot of stuff during those commercial breaks. And at that point, you notice that the light will get a little bit dim. Just so you keep that in mind. Now, another thing we'll have to look at here. Now, for electrical appliances, we have three connect the brown color code. The neutral has the blue color code, and then the F has the yellow. It can even be a combination of the two. So here you have the brown, that's for the life. We'll also talk about what each of this, what they do. You have the neutral wires, and then you've got the F, which on one side can be yellow and can also be green, or a combination of both. Now, the live wire, which is the brown, carries alternating potential difference from the supply. And then the neutral, it's just there to make sure that we have a complete circuit. And then the F is to guard against our appliance becoming live. Now, if you touch your refrigerator and you notice that it's you're getting electrical shocks, then you know that the F wire is faulty. The live wire has a potential difference between 0 and 230 volts. The F has a potential difference of 0, and then the neutral wire 2 has a potential difference of 0 volts. Now, the F wire, most times there's usually no current in the earth wire. The only situation where you can have current in the earth wire is when there is a fault, in the connection. Moving on, let's talk about power. When electrical appliances are connected into a circuit, energy is transferred to the appliance. And then there's what we term as the rate at which that energy we're talking about is transferred, and we call that the power rating of the appliance. You tend to see various appliances that have different power rating. To come across the pressing iron with a power rating of maybe around 2,000 watts, a refrigerator with a power rating of about 5,000 watts, or it could even be more. Bulbs, with a power rating of 60 watts, you've got 100 watts, bulb, depending on what you need. Now, there is an equation that you need to know, and that's the equation for power, which is power equals potential difference times current. And then we've got an alternative equation. Let's say, what do we know concerning
Ohm's law. We know that V equals IR, right? So we can actually substitute IR for V in this equation. So we have IR into I, and this becomes P into I squared R. So here you have an alternative equation. And just for the record, P is measured in watts, V is measured in volts, and then I is measured in amps. For this, R is measured in ohms. You know, that's the resistance. Now, let's say you have a question that says, we've got an electric kettle. Okay. Let's say we've got an electric kettle with a power rating of 800 watts, and then the voltage is 230 volts. Remember, the voltage is also the same as the potential difference. And the question says you should calculate the current. So go ahead and pause this video and calculate the value of the current. Now let's look at this together. We know that power, that's the electrical power, equals potential difference times current. And then when you make current in the subject, current is equal to power over potential difference. And you just substitute. Power is 800 watts, and then potential difference is 230 volts, and that gives 3.5 amps. Let's say we have a second example. The question says an overhead power line is 100 miles long and carries a current of 400 amps. Then the power line has a resistance of 27.5 ohms. Then we're asked to calculate the power loss. The power loss in the 100-mile length of the power line. Now all those values we have is just when the power line has covered a distance of 100 miles. That's what we're concerned about. With that, now you know the alternative equation, which is P equals I squared R. You have the current, and then you have the resistance. So it's kind of easy now. So that would be 400 squared times R. The resistance given on the question is 27.5 ohms. So that is 400 squared times 27.5. That gives us a value of about 4,400. Is that 4,400? That's 4.4 million watts. And then you can convert that to 4.4 megawatts. Remember, this value is for 100 miles of cable. So if we were talking about 200 miles of cable, that would be this figure times 2. How much energy is transferred? So appliances, they tend to convert energy from one form to the other. In fact, especially electrical energy appliances that work with electricity. So let's say for motors now, for electrical motors, what they do is that they take electrical energy, and they convert it, you know, once they start turning, they convert it into kinetic energy. Same thing for light bulbs, just kind of different. For light bulbs, they convert electrical energy to light energy, and then they also convert some form of that energy into heat, because once you touch a light bulb, you feel that heat. And then for electric heaters as well, they convert electrical energy into heat energy, and from time to time they tend to have different conversions, like for boiler ring now, for boiler ring or electric kettle, from electrical energy converted into heat energy, Now That on one side, that on one side. Now, when electrical appliances, um, when they convert energy from one form to the other, work is usually done on the circuit, and we define the work done in the circuit. That's the a level of energy transferred. So in this case, we can say energy transferred equals power times time. So let's look at it this way. We know that power equals work done over time. That's when we're talking about mechanical power. And then when you're defining that in terms of electricity, you can say power equals energy over time. Power can be equal to work done over time. It can also be equal to energy over time. So for this guy now, you can make energy the subject. That becomes energy equals power times time. And in this case, now, power is measured in watts, time is measured in seconds, and then energy is measured in joules. That on one side, we have an alternative equation, and that is energy equals charge times the voltage. The charge is measured in coulombs, the potential difference is measured in volts, and then energy measured in joules. So those are the two main equations we have to keep in mind. Let's say we have an electric motor that has a power rating of about 8 kilowatts, and then the main supply for this electric motor is mains supply. Let's say that is 230 volts at a frequency of 50 hertz AC alternating current, and then the charge flowing in the electric motor, if it flows for a time of 1.5 minute, how much charge do we have working or flowing in the appliance? Now, first things first, we know the values we have, and we have to convert all the values to standard unit before we even start working on it. 1.5 minutes, if you convert that to seconds, that's times 60, that gives you 90 seconds. And then power is measured in watts, not kilowatts. So we need to convert this. That's times 1000. All right. And then what's the equation for charge? That's energy equals charge times potential difference. Do we have the energy here? No. Do we have the potential difference? Yes. And how do we need to know the value of this guy. Now, there's a different equation that we can use to get the value of E. And that equation is energy equals power times time. So we use this first, and then this number one, and then we use this to get the value of Q. That's what we're doing now. So energy equals 8,000 watts times 90 seconds. That gives 720,000 joules. All right, now we have the energy, and all we have to do now is to plug the whole thing into the second equation. Energy equals charge times potential difference. Make potential difference, make the charge flow the subject. That gives you energy over potential difference, and that is 720,000 joules over 230, and that should give you 3,130 coulombs. So that's our answer right there. And then furthermore, let's talk about the national grid, because this is one question that you'll definitely see come up times without number. Now, what are the basic things you need to know about the national grid? The first thing is you've got the power station. That's where the whole energy and everything is produced. And then the energy in terms of the electricity now is now passed into the step-up transformer. Now passed into the step-up transformer, have that as step-up transformer, just have that as trans, and then after the step-up transformer, we'll have some high transmission lines. This is represented that by lines. Now the transmission lines, they're or what we call high tension cables, they're at a voltage of about 132,000 volts, or sometimes it could be even higher than that, So after that, we'll pass this whole thing into a step down transformer. Now it's on its way to the consumer now. So step down transformer, which operates at the rate of, the potential difference of 11,000 volts. It's still high, and there's no way that the consumer can use this amount of potential difference. So we need to still bring this guy down. So you've got a second step down transformer, which will now bring this guy down from 11,000 volts to around 240 volts, which is now passed into individual homes, consumers. So just you keep that in mind. Now, one thing you should know is that each of these transformers, they only affect the potential difference. Okay, not there's a direct relationship between the potential difference and the current, but let's just focus on what happens to the potential difference so that you guys will not be confused. Now, this is it. The step-up transformer will increase the potential difference. Let's just have V. The step-up transformer will increase the potential difference from the power station, all the way down to the transformer, right? And then also transmit that to the cables. So the power station's potential difference is not as high as what we need. So the step-up transformer will just come into play and then jack the potential difference up to around 132,000 volts or even higher. And then the step-down transformer will actually bring down the potential difference, decrease the potential difference, so that the consumers can actually use that. Now, I'm sure you must have wondered, why do we need to jack up the potential difference? The reason is that sometimes you can have power generated in a different state or a different country and sent to miles and miles and miles away. Now, we have two options available. Is either we transmit those guys at high current. Now, when we transmit at high current, there's a tendency that the cables will burn. Heat equals current squared times T. So if you transmit the electricity at high current, in that case, the heat will also increase, and the cables will burn and cause a lot of damage. But meanwhile, it's easier to transmit these guys at high voltage. At high voltage, we can actually have a wires move at different distances, and the distance can be really, really, really long without exposing our cables or even the community to so much danger. All right, now all what you have on the screen is not included in the national grid. The only thing you have in the national grid, you've got the step-up transformer, the transmission cables, and the step-down transformers. The consumer and the power station is not, they're not part of the national grid. So let's just keep that in mind here. The consumer and the power station are not part of the national grid. So if you have a question that says, oh, which of this is not part of the national grid, and you've got power station as part of the options, just pick that one out. Or if you've got consumers, both are not part of the national grid. One thing we also need to discuss here is what we call static electricity. From the start of this video, all we've discussed is current electricity. That's when charges flow when they move. What if we have a situation where the charge is static? We call the phenomenon static charges or static electricity. Now we've got two kinds of charges, electrical charges. You've got the positive charge, and then you've got the negative charge. Now, the rule is, when you have a positive charge and a negative charge close to each other, they attract. Remember the law, like poles repel, unlike poles attract. So this is unlike charges in this case. When we're talking about poles, we're talking about charges here. And then what if we have two charges that have the same sign? So two negative charges, they would actually repel. Like charges repel and opposite charges attract. So this whole thing, we term it as electrostatic forces. Electrostatic forces. Alright, so their non-contact forces is not most for these two charges to have, to touch each other. The main thing is once they're in each other's field, the effect will be felt. That's the main thing. And then how do we now produce static charges? Static charges, they tend to be resident on insulating materials. Or insulators. We have conductors, we've got insulators. So conductors, they allow free flow of electricity, and insulators, they make it difficult for current to flow through it. So when you rub two insulating materials against each other, they tend to become electrically charged, either positive or negative. And then when we say they become electrically charged, one of the insulating material will pick up electrons, and then the other will be left with positive charges. So the material that picks up electrons is what we can say that it is negatively charged, and then the material that loses electron, we can say that material is positively charged. Now let's look at the first case scenario that we have here. You're working on a carpet, and then there will be a buildup of charge once there is a friction between the carpet and the socks. Can actually cause a buildup of electrical charges. Sometimes it can be just the carpet and the socks, because the socks is also an insulator, or it could be the carpet and your shoe, because your shoe is also an insulator. So there can be once they touch each other, that's what we term by as charging by friction. Once they touch each other, there will be a buildup of charge. What you feel at that point, you just feel like a small spark or an electric shock. This is what you feel when maybe you touch the an appliance and you have just a slight electric shock. So in this case, looking at this now, the electrons from your socks or your shoes will move to the ground. It's more like your earth. Okay, the electrons will move to the ground, to the socks, and then the positive charges will stay on there. So it's more like here now you've got initially here you've got positive and negative charges. Then after stepping on the carpet, the negative charges, that's the electron, will leave your socks and stay resident on the carpet. That's when you've charged the whole thing by friction. That's one method by which we can charge materials. I mean, when we're talking about static friction. And then the second scenario is when you rub a balloon on your head. When you rub a balloon on your head, the balloon becomes charged. And what kind of charge are we talking about here now? The balloon picks up negative charges from your head. Balloon picks up negative charges on your head, and once you just move the balloon away, it's now negatively charged. And then when you just place it over a dust, the dust will kind of be attracted to the balloon. That's the main idea. And if you even proceed to place it on a wall, close to a wall, close to a jumper, you will see that the balloon will stick to the wall. The balloon will kind of like stick to the jumper. So what we did there is just to charge those appliances first, charge those materials, meaning those insulating materials, charge them first, and then rub them against each other.